Hello friends, now we are going to discuss the important 18 electron rule and its applications. The rule is based on the facts that the valence shell of transition metal consists of 9 valence orbitals, that is 1 s orbital, 3 p orbital and 5 t orbital, which are collectively can accommodate 18 electron as either in bonding or non-bonding electron pairs. This means that the combination of 9 atomic orbital with ligands orbital create 9 molecular orbital and that are either metal ligand bonding or non-bonding. When a metal complex has 18 electron, it is said to have achieved a same electron configuration as a noble gas in the period. The rule and its exceptions are similar to the application of octet rule in the main group elements. The rule is not helpful for the complexes of metal that are not the transition metal. But at the initially, the S and P block elements are also considered as the organometallic compounds. We can easily determine the difference between the EN and 18 electron count. In EAN, it is just the summation of all electrons of metal and the ligand, that is the atomic number of metal directly we can consider and the number of ligands, number of electrons donated by the ligand, that the summation of it is directly gives the EN number. For example, CrCO6, in which the chromium has atomic number 24 and 6 carbonyl ligands are there. So 1 carbonyl ligand donated 2 electron, therefore 6 into 2, therefore 12 electrons, and the total count become 36, and therefore the EN number of CrCO6, it is a 36. Whenever the EN number is 36, 54 or 84, then these molecule is called as stable molecule, because this is the same number which is the atomic number of noble gases, and therefore they are considered as a stable complex. Then in the case of 18 electron count, it is again the summation, but it is only the summation of valence electron of metal and the electron contributed from the ligand. That means in 18 electron count, we have to consider only the valence electron of atom, valence electron of metal. For example, again the same example we are considering CrCO6, in which chromium has the valence electron 6, and while 6CO contributes 12 electron, and therefore the total count becomes 18 electrons. Both rules are used to assume the stability of the complex. If 18 electron count is followed, then the complex is called as a stable complex. When the 18 electron rule is followed, then the complex is called as a diamagnetic complex, because all the electrons are in their pair form. The complex do not follow 18 electron count, then it is said to be a paramagnetic in nature, right? These are the simple thumb rule by which we can easily find out the different properties by using the 18 electron rule. Then the electron counting methods. There are two important methods are there, method A and method B. Method A is called as donor pair method and method B is called as neutral ligand method. In a donor pair method, we are considering the oxidation state of metal atom. While in the case of neutral ligand method, there is no any requirement to consider the oxidation state of metal. That is the major difference between method A and method B. I want to suggest one important thing to you, that you can determine either one of the way. If you are doing the study by method B, then up to the end you have to study by method B only, because otherwise it create a confusion among you. That is my kind suggestion to you, to remember or to do the practice by only one method only. One organometallic ligand are assigned an electron count and its charge. The charge of a ligand helps to determine the electron count of the metal. Add up all electrons of the metal d orbital and the ligand to find the total electron count. And we are considering the hydrogen. Hydrogen has, in a donor pair method, it is considered as a 2 electron donor, while in the neutral ligand method, it is considered as 1 electron only. While in the case of halogens, we are considering only one method. Now I am going to take only one method, that is neutral ligand method, method B. So halogens are contained 1 OH, cyanide CH3 all contain 1. NO, this is one of the important. When bent NO is there, metal and NO ligand, it is bent, then it is considered as 1 electron. And whenever NO is linear, then it meant contain the 3 electron contribution, right? Carbonyl, already we are stated, it is containing 2 electron for the donation. Then PR3 it is 2, NH3H2O2. Then carbene, it is also containing 2 electron. Then ethylene, it is a type of carbene, therefore 2 electrons. CNR, that is carbon nitrogen double bond is there, therefore it is again as like a carbene, therefore 2 electron. Double bond O, double bond, yes, it is 2 electrons again because double bond is there. So eta 3 C3H5, it is 3 electron. Then triple bond Cr carbine, 3 electron, nitride 3 electron, ethylene, and these again eta 5 C5H5, that is cyclopentadienyl, it contained by neutral ligand method, involved or it contributed 5 electrons. While in the case of benzene, it contributes 6 electrons. In eta 7 C7H7, that is cycloheptatrinyl, it is contain 7 electrons. This is the simple and thumb rule by which we have to remember the electron counting for all common ligands which are used in the organometallic chemistry. And these ligands, if you are remembering these ligands and their charge and their contribution of electron, definitely it will help to you to do the different carry out to do the study of all the organometallic complexes become very, very easy. Then we are going to do calculate the 18 electron count in the different complexes. First example, these examples are given in our well-known book, that is Inorganic Chemistry by Mishler and Tar, by Pearson publication. These examples I am taken from these for our sake of only study. Then ClMnCO5. The Mn it is in the first oxidation state. I already stated to you that method A, in which we have to consider the oxidation state of Mn. Whenever Mn has electronic configuration 3d5 4s2, it is normal state, so ground state. So whenever it is oxidation state is become +1, then 1 electron is less. That's why instead of 7 valence electron, we are considering 6 electrons. And then chlorine, in a donor pair method, the 2 electron contribution for chlorine, and in a case of carbonyl, these are 2 electron contribution again. Therefore, Cr minus 2 electrons and 5CO, 5 into 2, then 10 electron. So total electron count by method, donor pair method, it is become 18. While in the case of eta 5 C5H5 twice Fe, Fe has the electron configuration scandium, titanium, vanadium, chromium, manganese, and Fe. That means 3d6 4s2. So again, in a valence orbital, Fe contains 3d 4s2, 3d6. That means total 8 electrons are there. So it has Fe is in a +2 oxidation state, because therefore the 8 electron reduces to 6. So Fe2 plus, it contains 6 electrons. Eta 5 C5H5 minus. That is eta 5 containing 6 electron by donor pair method. So 2 eta 5 groups are there. It is a ferrocene, example of ferrocene. So 6 electrons, therefore 6 into 2, therefore 12 electrons. Total electron count become 18. While in the case of ReCO5 PF3 plus, again the same route we have to perform, only the additional is the positive charge. So whenever we are doing adding the positive charge, in that case we don't have any requirement is there. So there is the 18 electron count remain same. When this positive charge is considered already in the case of rhenium +1 oxidation state, it is mentioned in the oxidation state, therefore we are not considering the positive charge here, right? So remember this. Again, in method B, that is neutral ligand method. In Mn, it is normally it is 4s2 3d5. Therefore Mn becomes 7 electrons. So chlorine 1 and 5CO 10 electron. Total electron count easily become 18. Then in the case of Fe, 8 electrons 4s2 3d6. Therefore 8 electrons, valence electrons are there, and 2 cyclopentadienyl ring are there, which have eta 5, that means hapticity is 5. So 5 into 2, therefore 10 electrons, that the total electron become 18. In this simple way, in this way, we can easily calculate the electron count by 2 methods. Electron counting of choice is a matter of individual preferences. Method A includes the formal oxidation state of metal, while in method B, it does not. The method B is more simpler than method A. Then examples of 18 electron count. Well, I have given you the examples from which is asked in our CSIR-NET for 4 marks. The complex that does not obey 18 electron rule is. I have given the examples, number of examples to you. Among them, they are asking such type of questions for your computer exams. And it is very easy to solve the problem. The answer is 4. That is the which contains 17 electron for electron count. Then bonding in carbonyl complexes CO. Review of carbonyl complexes. Homo resides mostly and carbon double bond which includes S donation. LUMO resides only in carbon double bond which includes P acceptance and reinforce of each other provide strong bonding in which HOMO and LUMO are simultaneously form the bond to give the organometallic compound. The bonding in CO is first type is a sigma donation and second type is a pi acceptance. In sigma donation, there is the lobe is in sigma donation generally there is a donation of electron from ligand to metal, and in this case ligand is a species which can donate a lone pair of electron to the central metal ion. On this base, the ligand is considered as electron donor while metal is considered as electron acceptor. In the same way, whenever there is the same flow of electron from ligand to metal, then it is called as sigma donation. While in the case of pi acceptance, if the metal d orbital is slightly filled, then there is a possibility to the back donation of electron to the ligand also takes place. And whenever there is a flow of electron from metal to ligand, then it is called as pi acceptance. Please remember these concepts. Whenever there is a flow of electron from ligand to metal, it is called as sigma donation. While whenever there is a flow of electron from metal to ligand, it is called as pi acceptance. Overall interaction of these sigma donation as well as pi acceptance. Therefore, these terminologies sigma donation and pi acceptance are frequently used in the organometallic complex formation. Then characteristics of CO complexes. As far as this characteristic concern, we are using the different characteristic tools for it. Generally, by IR spectroscopy, we can find out whether the carbonyl is at the bridgehead position or at a terminal position. Whenever the free carbonyl stretching, which is at a terminal position, whenever CO is at terminal position, then it shows the significant peak at 2143 per centimeter. While whenever, for example, I have taken CrCO6, CO stretching is at 2000 per centimeter because it is slightly reduced. The standard value is 2143, but in CrCO6, it is found that 2000 per centimeter because p-back donation from metal weakened the CO bond by adding electron to the antibonding p orbital. Because of that, it is slightly reduced by 100, right? It has come up to 2000. Then one of the important assumptions we have to remember that the negative charge on a complex further weaken the CO bond. That means whenever any complex has containing negative charge, its IR stretching frequency get reduced. While whenever if the complex has carrying a positive charge, then its IR stretching frequency get increased. A simple assumption is there. Then bridging CO weaken the extra p donation, and this way there is the carbonyl bonding between the metal and the carbonyl is shown already here. The chart given is free CO shows the wave number 2143 per centimeter, while terminal CO shows 1850 to 2120 per centimeter. Symmetric CO, that means that a symmetric CO is there, it is 700 to 800, 1860. These are the important, on the basis of these 4 important values on which we can easily find out which CO is there, whether it is a terminal or a bridgehead or it is a symmetric, right? These are there. Another technique is of characterization is X-ray crystallography, in which free CO bond length is on the basis of bond length we can easily find out by X-ray crystallography whether the CO is terminal or bridgehead. That is important. Whenever the free CO is there, its bond length is 112.8 picometer, while in the case of MCO bond length is 115 picometer. Right? These are all the characteristic techniques which are used in the organometric chemistry. In the next video, we are going in a detail, more and more detail. Till then, thank you to all.